Okay, so let me just open um, open my yesterday's slide. Okay, so share my screen. Okay, okay. So we were talking about the probability distributions. Remember, especially the normal distribution. So just go back a little bit. Just okay. So we say that well, there are so we we just started by saying that well, we are just working on populations, okay? Populations. So what's a population? I just come here. Population was the collection of all individuals or observations of your interest, okay? So for example, students in Özyeğin University is a population, or the products coming out of a factory is a population, or people in Turkey is a population, or people in the world is a population. So population is something that is related to your interest. Um, so uh, there are two important characteristics of a population, okay? Um, so if you are, for example, if we are dealing with height of the students of Özyeğin University, okay, then there are two important measures for the height. The first one is its mean, okay, and the second one is its variance. The mean just shows well what is the average, okay, what is the average of the data, and the variance just shows you well what is the deviation around the average, okay. So these two important measures and the statistics course, we will try to deal with these two important characteristics, okay. So in general, for example, if you are just dealing with the mean or the deviation or the variance of the population, for example, let's talk about the average height of the students in Özyeğin University. Well, it's either um, sorry. So I just hear voices when just people come in. I just want to cancel it, but well, okay. Sorry. Okay. So okay. Um, so finding the average of all of the students in Özyeğin University is either impossible. If it is not impossible, it's very expensive. So what we do is, remember, we just take samples, okay? So for example, there are 10 students in this Zoom session, okay? So we are a sample of our target population. So the sample is our class. The target population is the students in Özyeğin University, okay? And we're interested in the height of the students in Özyeğin University. So what we hope is that, well, we just hope that this sample will reflect the general characteristics of the population. So it should be an unbiased sample. What do we mean by unbiased? So for example, if you just go and take your sample from the basketball team of Özyeğin University, then it's not a random, it's not a unbiased sample. Why? Because, well, these guys are playing basketball. So as you expect, these guys are just selected from the students whose height is higher than average, okay? They are taller than average. So the sample should be a random sample so that but it just reflects the characteristics of the population. Okay, so um, in order to find these characteristics, okay, the two important characteristics, the expected value, the mean, the average, and the deviation around the average, which is represented by the variance, or remember, we just take the square root of that, which is sigma, the standard deviation, okay? So in order to find this well, we have two measures, okay? Um, so we have this x bar, remember this is the average of the sample, and this is the s square, this is the variance of the sample, okay? So remember we also have mu, right? We also have mu, okay, mu. We also have sigma square, but mu and sigma square just belong to the population, okay, to the whole school, but x bar and s square just belongs to the sample that we have, right? So, okay, in the recitation, you will just make some examples regarding this x bar and finding x bar, finding mu, s square, and sigma square, so that it will be much more clear for you about what is s square, what is sigma square, what is the connection between them, and what is difference between them. But in general, sigma square is, again, remember, sigma square is the parameter of the population, but S square is the parameter of is a measure for the variance for the sample. Okay, so the whole story is, well, we are interested in the population. Okay, we are interested either with their mean or their variance. Okay, but it's impossible to find them most of the time. It's impossible or very, very expensive to find the real mean and the real variance. Okay. So what we do is we just take a sample and calculate x bar, which is the sample mean, and we just calculate s square, which is the variance of the sample. Okay. And X bar will give us information about the real but unknown parameter mean, and S square will give us information about the real but unknown parameter sigma square. Okay, so we don't know mu and sigma square. It's impossible to calculate them. But what we do is we just calculate the sample mean and sample variance to just extract, to infer, to get some information about the real parameters mu and sigma square. So remember, we said two things, two important things. The first one is, well, mu and sigma square, they are parameters of population. They are constant, okay? They don't change from sample to sample. They are constant. They don't change from sample to sample, okay? But x bar and s square, they are, remember what did we say about them? X bar and S square, so just concentrate on X bar. X bar is the average of the sample. So if we are talking about uh, our Zoom session, okay, as a sample, now there are 10 students here. I don't know how many students do we have. 11, 10 students, okay? So these 10 students are if you take the average of them, this is X bar of our class, okay? So assume that, well, there is another class, I don't know, probability class, I guess there is a probability class, Ismail Hoca's class, right? So let's say there are 10 students there as well. If you just take the average of them, by average, I just refer to the height, okay? Now, I will use the height example throughout the lecture. So when I refer to students and mean and sigma square, most of the time I just refer to the heights of the students, okay? Right, so X bar of our class and X bar of Ismail Hoca's class, well, they are different because it's the average of this class and it's the average of the other class. So what they expect to see is they are different, okay? And similarly, S square of our class and S square of Ismail Hoca's class are different. This is because these are random variables. X bar and S square are random variables. Why? Because X bar is the average of 10 many students. Okay, in our example, we are talking about 10 many students. So each student's height is a random variable. Any function of a random variable is a random variable itself, right? And S square is a function regarding just using 10 many students. Let me, okay, just go back. Remember the S square function. See this? Xi is from 1 to n minus x bar squared divided by n minus 1. So this is a function of random variables, 10 many students. So Xi's are the height of the students, x bar is the average of the average height of the students. So this is a function of random variables. This is a random variable itself, right? Hence, we can see different values at each class. But mu and sigma square of our class and Ismail Hoca's class are the same. because mu and sigma square does not belong to a particular sample, they just belong to the population. Okay, so the population is Özyeğin University, and the sample, our class is one sample, Ismail Hoca's class is another sample. Okay, so our mean and their mean are the same. So you can think of this as, I'm just giving the same example in my lectures. Just think about a factory. Okay, so this is a factory. Sorry for bad writing. I haven't received my Wacom tablet yet. So next week, probably I will have my tablet so that I can just write better. This painting, just like my son's painting. Okay, he's 4.5 years old. Okay, just okay. So this is a factory. This factory just produces students. Okay, the first student, another student. So each student has different height. Okay. So this is just like they just produce 10 students. 10 student is our class. So this factor produces another 10 students. Those 10 students are another class. Okay. So each student is a random variable. Their height is a random variable. Okay. And x bar of each class is a random variable because it's a function of random variables. And being a random variable means that x bar has a mean itself, x bar has a variance itself, and x bar has a distribution itself. Okay, so just like every random variable, x bar and also s square, they both have an expected value, a variance, and a distribution function. Okay, so this is a bit weird when you just first think of this. Well, x bar, its sample mean, the sample mean has a mean itself and the variance itself. S square, it's the sample variance. It has a mean itself and it has a variance itself. Okay, so the sample variance has a variance itself. Okay. So we just say that, well, what is the expected value of x bar? Expected value of x bar after some algebra, you can show that, well, expected value of x bar is equal to mu. Okay. And we show that expected value of, not expected value, sorry, variance of x bar is equal to sigma square divided by n. Okay. Sigma square divided by n. What is sigma square? This sigma square is the variance of single student. Okay, not single student, sorry, but it's the variance of the distribution of single students. Okay, so what does this mean? This means that, for example, if you have, let's say, 1 million many students, okay, you can just measure their heights and make the histogram. Remember, we talked about histograms yesterday, and just make the histograms in a very tiny buckets. Then you will have this distribution. So this is the distribution of single students. Well, the distribution's variance is sigma square. Okay, this one is sigma square. Now, if we just let's again talk about the class of 10 many students. Okay, let me just change the color of the pencil. Now, sigma square divided by n, right? This is the variance of x bar. What does it mean? It's the variance of one guy plus another guy, okay? Plus dot dot dot dot dot. I have another guy here divided by 10. Okay? So this variance belongs to this variable. What does it mean? How can I find this? Well, what you can do is, again, if you can just produce 1 million many X bars, how to produce them? It's easy, right? So again, just think of the factory that we have. Just think of the factory that we have. In the factory, just produce 10 students. Take their average, that's my first X bar, right? Then produce another 10 students, take their average, that's my second X bar. Like this, produce 1 million many. Of course, 1 million, well, that's what I'm trying to say is you can produce too many variables so that you can find the real mu and real X bar, right? And X bar, let's say this is 1 million. Then, if you just take the average of these, right? It turns out that this average is equal to mu, okay? And so again, this one has distribution like this, and this distribution uh, has a variance of what? Sigma square divided by n, okay? Right? So this is, again, let me just put the red one. This is the variance of the distribution of single guys and sigma square over n, sigma square over n. This is the variance of the distribution of X bars. Okay? Again, how to find the distribution of X bars? If you have a factory that produces students, then generate as many as X bars as you can. For example, generate 1 million many X bars and make a histogram, then you will see the distribution. Again, you can just make the same thing here, right? You can produce 1 million many students and make a histogram, you will see its distribution, okay? So if you want to see the distribution of any random variable, then produce as many variables as you can and make a histogram, you will see the distribution itself, right? Now, okay. So the variance of X bar is sigma square over n. Its expected value is mu, that's fine. Well, what is the distribution of X bar? We have a great result, okay? So the great result says, the name of the great result is central limit theorem. And central limit theorem says that, well, X bar, remember, we say that X bar, its mean is mu, right? Its variance is what? Its variance is sigma square divided by n, okay? So up to now, we don't say anything about the distribution of X bar, right? So if the distribution of your height is uniform, for example, it doesn't affect this result. So still, its average is mu, and its standard, its variance is sigma square over n. So these results does not change with the distribution of single student's height. Now, we just come to another conclusion, as we say. So central limit theorem. Central limit theorem says that, well, X bar is approximately normally distributed with this mean and with this variance, okay? This is a great result. Why? Because it says that, well, the distribution of X bar is approximately normal uh, regardless of the distribution of the individual students, right? So if your height is uniformly distributed, still your average will be normally distributed. If your height is, I don't know, exponentially distributed, still your average is normally distributed. If your height is, I don't know, gamma distributed, still your X bar, your average is normally distributed. Okay, so this is a great result. Of course, this is not exact distribution. Uh, this is the limiting form, which means this is an approximate distribution, but it works. Okay, it works most of the time. Again, in the recitation, you will solve some questions regarding the central limit theorem and the distribution of X bar. Okay, then we solved an example. Remember, an example about the central limit theorem, and we say that, well, let's, by the way, so the distribution of X bar, we say that, well, it's approximately normal, but we can say that the distribution of X bar is perfectly normal if the distribution of the individuals are normal as well, okay? So if your height is normally distributed, if the height of an individual student is normally distributed, if the heights come, let's say, comes from a normal distribution, right? Then X bar is perfectly normal. You don't need any central limit theorem. But if they are different than normal, then central limit theorem says that, well, it's approximately normal. What does this mean in terms of our factory? Okay, let's say this is our factory, just produces students. It says that if the factory is producing, so if the products, right, if the products are produced using a normal distribution, right, then the average of the students, the X bar, is normally distributed as well. But if the factory is producing using a non-normal distribution, and exponential, it may be exponential. Let's say if this is normal, then the height is normal as well. Okay, again, sorry for bad writing. Normal. But if the factory is producing, let's say, non-normal, which means it may be uniform or exponential or gamma or anything you wish, then, so from central limit theorem, we can say that X bar is still normally distributed, okay? That's something great. Okay. Then we say that, well, let's look at, sorry, we have a question here. The question says that, so in order to understand, not central limit theorem, but in order to understand what do we mean by the variance of X bar. So assume that the heights of the students in the Özyeğin is distributed normally, with mean is equal to 170 and sigma is equal to 10. Then what is the probability that the student coming to this Zoom session, okay, is shorter than 165? So let me just define X as the random variable which shows height of a student, okay? Height of a student. This is height of a student, okay? Of a student, let's say. Then this question asks, what is the probability that X is what? X is smaller than 165, okay? So how to solve this? Well, if you have a normal random variable, what you should do is directly just convert this to standard normal, right? How? This is equal to probability that, remember, X minus mu of X, which is 170, divided by 10, smaller than 165, right? Minus 170 divided by 10. And this is Z, okay? This is Z, probability that Z. Remember, what was Z? Z was the standard normal random variable, which has the tables at the end of the book. Z is smaller than minus 5, this is minus 0.5. And you can just look at the probabilities, which was, remember, it was something like 0.31, right? And the next question, what is the probability that the average height of a class with 25 students is shorter than 165? Now, what does this question asks? This one asks, what is the probability that your X is smaller than 165? Is that true? Cenk, is that true? Is it X or? Hmm? Cenk, yes, I just read your question now. Recitations will be recorded as well, and they will be uploaded. So at first, I just talked with my TAs. Probably there was a misunderstanding. So he just understood that I told him not to record them, but now we are okay, right? So Ahmet will record, and Ahmet and Doruk, they will just record the recitations, and they will just put the links or the videos to somewhere that you can have a access, okay? Right? Okay, Cenk. So probability that X is smaller than or equal to 165, is that right? Probably not, right? Because A and B is the same. So we will not probably solve the same question. This is, now read the question again. what is the probability that the average height of a class with 25 students is shorter than 165? So it just asks, well, the average height of a class. So the average height, what is the average height? That's the X bar. So the first question asks, well, if somebody just enters the Zoom session, what is the probability that his or her height is shorter than 165? Okay, so this was the first question. Now the second question asks, if 25 many students just join this Zoom session, okay, 25 many students join this Zoom session, what is the probability that their average is smaller than 165? Now, my question is, what do you think? Is this probability, is it, the first probability was 0.31. Is it equal to 0.31 or smaller than 0.31 or larger than 0.31? What do you think? Okay, so, well, so this is, okay, just think of this. The average of the distribution, the height of the students has a mean of 170. Okay, so the probability that a single student is less than 165 is 0.31. Okay, this is the probability that we have found. Now the next question asks, what is the probability that the average of 25 people? So the average of 25 people, what do you think? So it should be closer to 170, right? Because it's the average height. So this average height should be close to 170, which means the probability that X bar is smaller than 165, probably that should be smaller than 0.31, okay? Well, it was indeed. The result was something 0.006, right? It is very, very smaller than, too far beyond smaller than 0.31. How do we find again? Well, X bar is normally distributed, okay? Well, it's normally distributed because the distribution of X is normal, right? But even if X is not normally distributed, we can say that X bar is approximately normally distributed. How? From central limit theorem, okay? So how to find this probability? Remember, we said probability that X bar minus mu of X bar, which is 170, okay, divided by 10, divided by root 25, okay? Why? Because what we are doing here is that, well, X bar is normal, we just subtract its mean, which is 170, and divide it by its standard deviation. What is its standard deviation? Remember, the standard deviation of X bar is sigma divided by root n, okay? 10 divided by root 25. Just do the same transformation to the right-hand side, and you will see that the resulting probability is 0.006. Right? Great. Okay. Now about the normal distribution. Well, so I hope we are comfortable with this. If you're finding the probability, just standardize it and use tables. Okay. And we have parameters and so on and so forth. Well, one last thing to say about the normal distribution is that we have a different notation for normal distribution, okay? Z sub 005, Z sub 005. What does this mean? What does this mean? Let me just plot the standard normal distribution. This is the standard normal, okay? So its average is 0. Its average is 0, right? Its standard deviation is equal to 1, right? And Z sub 005 is this. This is the Z sub 005. 0.05. So this means that, well, this is the z value which leaves an area of 0.05 to the right, okay? So it means that, well, this area here is 0.05, okay? This is not something new. There is no calculation here. This is just a notation, okay? So we just show some z values by just writing a subscript to them. So z sub 0.005 is the value which leaves an area of 5% or 0.005 to the right, okay? Um, okay, so I have this painting. You see this? So let me just erase this. Okay, so I have a good picture here. So you see this, well, this area here, so remember, the whole area, okay, sorry, the whole area under this curve was equal to 1. Remember, so the integration from minus infinity to plus infinity, which corresponds to the total sum of the probabilities, is equal to 1. So what you do is just look at this number, okay, which is 1.645, and the area here is, let me just plot this, the area here is, okay, this area, this is equal to 0.05, okay, and this value is 1.645, okay, 1.645. So this value is equal to 0.z sub 0.005, okay. Well, this is the z value, which is equal to 1.645, which leaves an area of 0.05 to the right. So what does this mean? What does this mean? What is the area to the left, or how can you write this? What is the probability that your standard normal z is smaller than z sub 0.005? What is this probability? So this probability is simply, um, this probability is simply the area, okay, to the left of this z value, to the left of z sub 0.005, okay, this area. What is this area equal to? This total, all this area, right? To the left of z sub 0.005. This is equal to what? 0.005? No, this is the area to the left, right? The area to the right is 0.005. So the area to the left is 1 minus 0.005, okay? Which is equal to 0.90, sorry for again bad writing, 0.95, okay? Right? So let's check this from our book, okay? So let me see if I just have the book. Right here it is. Let me just go to the statistical tables and proofs. Table A3, right? A3. See this? Let's look at this part. So, okay, let's look at here. See this? So 0.9495, 0.9505. So this one just corresponds to 1.60, 60, 61, 62, 63, 64, and 65. So in between you have 1.645, okay? So let's see if I can just write here. So here, this is 0.95 is here, okay, somewhere in between. Okay, somewhere in between, 0.95, it's somewhere in between. And it turns out that this value is equal to 1 point, sorry, 1.645. Okay, so from this table we can say that, well, I can just write this. Let me just again, no, let me just move it here. So the probability that, no, so let me just write it here. The probability that z is smaller than 1.645, okay, is equal to 0.95, okay, which means, well, which means z sub 0.05. What does it mean? Z sub 0.05, the z value that leaves an area of 0.05 to the right, which means it leaves an area of 0.95 to the left. So this is equal to 1.645. Okay, great. So for example, if I just ask you by just looking at this table, well, what is, let's say, what is, let me just ask you, what is z sub 0.14? Can you find it from this table? Let's find the approximate value. I just don't ask you the exact value, but what is z sub 0.14? What is the value of z sub 0.14? Okay, so today we have 11 friends, okay, watching the lecture. Thanks for coming, all of you. Okay, I have an answer there. 1.101. Let's see. 1.01. I don't know the result. Just close this. 1.01. 1.0. 1.1. 0.14. So this is not 0.14, I guess. 1.08. Let me just check. 1.08. 1.08. It's here. So probably this is much more better than the first answer, okay? Yes. Why? Because this is almost 0.16. Sorry, 0.86. Okay, this one, 0.86. So this z value, so this is equal to the probability that z is smaller than z sub 0.014, sorry, 0.14 is equal to what? 0.68, right? Now what I will try to do is just look at the table and try to find 0.86. And 0.86 is, as your friend said, it's just here, 0.86, right? So hence, the value of z sub 0.14 is equal to what? Is equal to 1.08, okay? So thanks, Faizan Dilayda. That's the correct answer, okay. So let me just ask another thing. So let me say, so for example, what is, let's say, um, okay, what z sub, let's say 0.16, okay? Now what is the value of z sub 0.16? And okay, I want just, so I have a table there, up there, but I won't open that one. We will still remain here, okay? Any guess? Z sub 0.86. So, okay, let's do it together, okay? So let me just open this. Even open minus 3.63. We have an answer. Great. So, sorry. Okay. So there is a poll in the Zoom. So, okay, that's not a good idea, I guess. Minus 2.19. So, okay, let's check both of them. Minus 2.19. Let me just open this one. Minus 2.19. So just come here. Minus 2, what is that? Minus 2.1. Minus 2.19 is somewhere here. Okay, so this is the result. 0.0. So Beza, probably you just take one additional zero there, right? 0.014. It's not 0.014, it's 0.14, okay? So I have minus 2.2, again, that's 0.014. So I guess you just added an additional zero there, okay? So this is Z sub 0.16, which means, so it leaves an area of 0.86 to the left, okay? So what does this mean? We can just write it like this: probability that Z is smaller than Z sub, so in fact you are on the right way, but you just make a small, let's say, um, operation error, let's say, the probability that Z is smaller than Z sub 0.16 is equal to, sorry, not 16, but 80, 86. That's equal to what? 0.14, right? It's not 0.014. So, okay, that's great. So let's look at minus 1.08, minus 1.08, minus 1.08. It's here, right? Did you see this? 0.14. So the result is minus 1.08. Okay, thank you. So, well, do you see any connection with the previous question? Remember, we said that 1.08, it's somewhere here, okay, this one. So the result for the previous question was 1, so let me just check. Z sub 0.14, that's equal to 1.08, okay? And I have Z sub 0.16, which is equal to minus 1.08. You see the trick? They are just the, let's say, positive and negative part of the other, okay? So why is that true? That's true because, well, 32. Let me just talk about some, give a break, 10 minutes break. So let me just stop the share here and um, share the other screen. Okay. So that's because think of this standard normal, okay, this one, this is 0, right? This is 0. And we say that, well, here I have Z sub, what was that, 0.14 or 16? Was it 14, right? 14. Let me check. 0.14, yes, that's true. 0.14, which leaves an area of what? 0.14, right? To the right. Okay. And this was equal to 1.08. Well, the thing is that normal distribution is symmetric. It's symmetric around its mean. So standard normal, it's also symmetric around its mean. It's symmetric around 0. What does this mean? So if we just take this one and put, let me just change the color. Put it here, just like as if there is a mirror here, okay? Then this area is what? 0.14, okay? And this is what? This is in fact minus z times 0.14, which is in fact equal to z sub 0.16, right? So this is in fact what? This is in fact equal to z sub 1 minus 0.14, okay? Again, why? This is because the standard normal is symmetric, okay? So once you have found any z sub value here, you can just multiply it by a minus and find the, let's say, found the other version in the other quadrant of the normal distribution. This is again 0.14, this is 0.14, this is z sub 0.14, which is 1.08. This is minus z sub 0.14, which is equal to minus 1.08, okay? Which is also equal to z sub 0.18, right? So in general, we can just write this in fact. Z, okay. Um, So this is z, let's say this alpha, z alpha is equal to what? Minus z times 1 minus alpha, okay? So for in our example, z sub 0.14, okay, which is, remember, it's 1.08, that's equal to minus z sub 1 minus alpha, which is 0.68. Remember what is this? This is 0.68 is equal to minus 1.08, and minus it's equal to a plus, so this is true, right? So you can just write z alpha is equal to minus z 1 minus alpha, okay? Any question? Right, so let's give a 10 minutes break, okay? And after the break, let's meet and continue with our lecture, okay? Now I will just pause the recording, and after the break, we will continue the recording. Okay? Yes. Recorded. Okay. So as I said, the last thing is sorry. Okay. So again, the last thing is, well, you have sorry everyone. Efendim. Hocam dersteyim ben ya, kusura bakma. Okay, so the last thing that we cover is, well, this the normal distribution have a different notation, which is shown by sub, which is shown by numbers using the sub, let's say, using the subscripts. So I'm just trying to show another thing here. Okay, this one. Okay, so for example, z sub 005 is the z value, okay, is the z value, which gives an area of 0.05 to the right, and its value, as we see, it was 1.645. Z sub 010, its value is 1.282, okay, and z sub 001, its value is 2.326. As you see, so let me just plot this. So let's say this is the standard normal graph, okay. So this is, here I have z sub 001, okay, z sub 001. So it's equal to 2.2, sorry, 326, okay. And the area here is The area here is what? It leaves an area of 0.01 to the right, okay? This is 0.01. And let me just change my color. Z sub 005, which is somewhere here, hopefully. Z sub 005, okay? And its value is 1.645, 1.6 and 4 and 5, okay? And the area here, okay, here, the area here is up to z sub 001. So the area to the right of z sub 005 is 005. And the area here in the red region is 0.01, hence the remaining region is what? The remaining region is 0.04, okay? So if you just sum them up, 0.00, 0.04, 0.01, their summation is equal to 0.5. And let me just pick this blue one, okay? So let's say this is z sub 01. 01, okay, which is equal to what? 1.22, sorry, 82, okay, and the area to the right of this, up to the green region, up to the green shaded area, this is equal to what? So the area to the right of z sub 01. Sub-Zero was a character in what? In Street Fighter? No. In what? What was that? What was that game? There was a computer game, right? Sub-Zero. Okay, I didn't remember. If you remember, you can just write it. So Z sub 01, the area to the right of Z sub 01 should be equal to 0.10. So to the right of this one is 0.05. So what's left is here I have 0.05. Okay, right? So the area to the right of 0.1 is 0.10. To the right of 005 is 0.05. To the right of 0.001 is 0.001. Okay. So in fact, this is what you can see in terms of the Z sub values. These are in the future lectures, we will see that these numbers are very widely used. Okay, Z sub 01, Z sub 005, and Z sub 001. Okay, great. Okay, so now, okay, let's start with some other, let's say, with the other slide. Now I will just open the slide H14. Okay, the statistics for measuring. And now we will talk about, so we said that there are two important measures. Remember, the centrality and the variability, which is the dispersion, the scatter around the mean. And we said that there are two important, so there are two measures, let's say there are two statistics to measure them. X bar is the average, which measures the center, and sample variance S square, it just measures the variability. But they are not the only statistics, okay? We have some different statistics as well. We will see. If I can proceed, we can see. Okay. So sample mean, as we say, so it's one of the measures that we use for just calculating, let's say, the centrality, the central tendency. Right? The other one is the sample median, right? Sample median. So what is median? Well, what you do is you first order the numbers that you have. So for example, if I just ask you your heights, then what I do is I just order your heights, okay, from the smallest to the largest. Then sample median is is just the one in the middle, okay? Little in the middle is the one that's in the middle. So if it is an odd, if n is odd, so here we have how many participants do we have? 10 participants. One of the participant is me, so there are 9 participants, okay? So if I just ask you your height and ordered you, then the fifth observation is our median, okay? Sample median, right? If n is even, what does it mean? So if I just add my height to the sample, okay, or let's say I don't add myself, but let's assume another guy just attends the Zoom session so that we have 10 students here, then the average of the fifth and the sixth student is our median. Again, median is it's a statistic. Remember the statistic? What is the definition of the statistic? It's a function of the observations, okay? So sample median is also a statistic, and it shows, it measures the central tendency. Okay? For the variability, remember the variance, the variability, the scatter around the mean, we just talk about the sample variance. Another one is called the sample range. So what is sample range? Well, it's simply, again, you just order from smallest to the max, from smallest to the largest, and the difference between the maximum and the minimum value is your range. Okay. And of course, we know the sample variance, it's the xi minus x bar squared divided by n minus 1. And remember, what is this? So the summation is, so we just make some example on the Excel, remember? So this is this is, if we have 10 students, this is the average of 10 students, and this is the observation of any student. What we do is, we just look at the difference between the average and an observation, take the square of it, right? And sum all of them. So in fact, this is the, let's say this is the somehow total variance, okay? So you just sum all of the differences between each observation and the mean. This is called the total variance. Then what we do is, we just divide it by almost, so don't get stuck with this n minus 1, but we just divide it by the number of observations, so that we just find the variance per observation, okay? The variance per observation. That's my S square. If you just take the square root of this, which means you will almost finding xi minus x bar, okay, if you just take the square root of this, then it just shows you the standard deviation. Okay, now the name implies, the name has a more meaning, or let me say, when I first discovered this when I was a student, well, I then understand why they call this as standard deviation. This is because standard, why you just sum all of the variances and divide it by the number of observations. So just you standardize it. And this is deviation because you just find the deviation around the mean. Okay, so this is standard deviation. Okay. Well, the first thing, this is the definition of standard deviation, but the second part, the second formulation is exactly the same, but we generally use the second one, okay, this one, when we are calculating it by hand. Okay. Now let's make a small example. Let's find the sample mean, the sample median, the quartiles, and the sample standard deviation for the following data set. Okay. So it is 3, 5, 3, 7, 6, 6, 8, 5, 7, and so on and so forth. So there are 15 numbers here, and the sample mean is simply just sum all of them and divide it by the number of observations. So the sample mean is 5.67. So in order to find the sample median, what we do is we just order them from smallest to the largest. You see, 3, 3, 4, 4, 5, 5, 5, 6, 6, 6, 7, 7, 7, 8, 9. Right? Now what we will try to do is find the one just in the middle. Remember, how many items do we have? 15 items, okay? 15 items. So I will just find the one which is the eighth one. 1, 2, 3, 4, 5, 6, 7, 8. right? This is the one in the middle. So the median is equal to 6, right? How about the quartiles? Quartiles are in fact, so I have the lower quartile and the upper quartile, okay? So the lower quartile is simply, you just take the first half of the data, okay? This is my first half, right? And this is my second half. Then what you do is you just find the quartile, the median of the first half and the median of the second half. The median of the first half is your first quartile, which we call as Q1, right? And the median of the second half, the upper half, is called the third quartile, okay, Q3. So here, again, Q1 is the median of the lower half of the data, okay? And upper quartile is the median of the upper half of the data, and that's Q3, then that's 7. Okay. And in order to find the sample variance and also sample standard deviation, what we do is we just calculate. Remember, we have a formula. I don't recall the formula. I don't memorize it, but I just memorize the first formula, this one. I know this one, but I don't know. I don't remember this one. So I need xi squared and sum of xi's. If you know both values, xi squared and xi's, then you can calculate the sample standard deviation. Okay, let's see this. The sum of xi's is 85. Sum of xi squared is 525, right? And it turns out that, well, the sample variance is 3.095. If you just take the square root of this, the sample standard deviation is 1.76. Again, what does this mean? This means that on the average, our sorry, I just forgot what is the sample mean. Okay, 5.67. Okay, so my average is 5, right? 0.67. So this one says that on the average, your data just deviates around the mean by 1.67. So this is the standard deviation, right? Remember how we found this? This is just xi minus x bar, right? Divided by almost the number of observations. Of course, this is squared, and you just sum them up, right? So this is the squared deviation per observation, and then you just take the square root. So this 1.76 shows you the standard deviation around the mean, which is 5.67. And what is the sample range? It's simply the difference between the maximum value and the minimum value, which is equal to 6. Okay, 9 minus 3, that's equal to 6. And we also have another definition, which is called the interquartile range. Okay, that's equal to the Q3, the upper quartile, and the lower quartile, which is equal to 3 as well. Okay. Now, let's look at this data. Let's look at this data. So in the first sample, I have 3, 5, 7, which is equal to 5. In the second sample, I have 1, 5, 9, and its average is 5 as well. Okay. And this is the third sample, 103, 105, 107, and its average is 105. Now, my question is, without making any calculation, what can you say about the variance, or what can you say about the standard deviation of the first sample and the second sample? Okay. Again, what can you say about the standard deviation of the first sample and the standard deviation of the second sample? Okay, so second sample has a higher standard deviation. Why? If you just look at this one, okay, so if you just want to plot, let's say, put them on a graph. So the first sample, let's do it with red. So let's say this is, I have, let's say this starts from 1. Let's say I have 3 here, I have 5 here, okay, I have 7 here, and I have 9 here. So this is my axis. Then, so the first sample, I have one sample here, one sample here, and one sample here, okay? Now let's look at the second one and just plot it with green. So the second sample, I have one sample here, another sample here at 9, and another sample here at 1. So as you see, the second sample has, so when you just look at this by inspection, with your eyes, so you can see that, well, the data in the second sample, okay, the data in the second sample has a larger scatter, right? Larger deviation around its center. So if you just look at the first one, right? If you just look at the first one, you see that, well, the dispersion, the scatter is smaller than the second one, right? So you can directly say that, well, the first one has clearly a small standard deviation, has a smaller standard deviation than the second one. Okay, that's great. Now, what can you say about, for example, the first one and the third one? Okay, sample 1 and sample 3. Which one has a larger standard deviation or smaller, or can you say it without and making any, let's say, calculation? The second one, right? So if you compare it with the first one and the third one, 1 and 3, um, well, 1 and 3, so let's assume I just make the same plot here. Let me just put the orange one. Okay, let's say this is 105. Okay, this is 103. So 107. Sorry, and this is 103. Okay, right. So one data is here, one data is here, one data is here. Right. So if you just compare it with this one, is there any difference in terms of variance? Not really, right? Because, well, what you do is you just take this red part and move it along the axis and just put it on the top of 105, right? So in fact, both data has exactly the same standard deviation. Their mean is different, okay, but their standard deviation is the same, okay? So it turns out that, well, the standard deviation of the first one is 2, the second one is 4, and the third one is 2 again. You can just calculate it at your hand. But it turns out that, again, the standard deviation does not reflect the magnitude of the sample data, which means it doesn't reflect the, let's say, position of the data, okay, whether it's at the very close to the 0 or it's close to higher levels or so on and so forth. It just shows the scatter above the average, okay? It just shows the scatter above the average. Okay. Now we have some data plots. Well, in fact, we have seen some of them. Remember, we just see the histogram, right? So let's make an example here. So the interior temperature, sorry, of a drying oven has been measured every 15 minutes for the duration of one production cycle, and the following data are obtained. You see, so there are a bunch of data here. 56, 46, 48, 50, 40, and blah, blah, blah, blah, so on and so forth. So when you just look at this data, it's much more clear that why we need data plots. Okay, why we need data plots? We need the data plots because when you just look at the numbers, well, they're only numbers. You cannot understand anything um, if you don't have any, let's say, supervision. When you just look at the numbers, They are only numbers. Okay? So visualization, data visualization is very important. By just visualizing your data, you can understand what is the center of the data, what is the behavior of the data, is it inclined to the left or right, is it skewed to the left or right, and so on and so forth. Okay. Okay, so what we do is, first we make a frequency distribution of temperature data. How? How? So what we do is, well, just find the number of temperatures between 30 and 35, okay? So just come here, 30 and 35. Look at here, 30, 35, 35, 35. Here I have 32 here, right? And no more, right? Only 32, okay? So how many data are between 35 and 40? So just look at this note. The lower interval limit is included, okay? The lower interval limit is included, and the upper limit is excluded. So it means that, well, 30, 31, 32, 33, and 34 are in this interval. 35, 36, 7, 8, and 9 are in this interval. And 40 up to 44 are in this interval, and so on and so forth. Okay. Okay, great. So what we do is we just count how many recorded data are in between 40 and 44, how many data are in between 45 and 49, and so on and so forth. So this is the frequency table that we have. Okay. So let's see how many of them do we have. This is 10, 30, 40, 51, and 55. There are so 55 mini data, right? Okay, and this is the cumulative count. So cumulative count, so if you just make an analogy to the probability distribution, this is just like the CDF, right? So how do you find the cumulative count? 1 plus 3, that's equal to 4, 4 plus 11, that's equal to 15, 15 plus 18, that's equal to 33, and so on and so forth. And here we have the percent. How do you find the percent? 1 divided by 55, right? 3 divided by 55, 11 divided by 55, and so on and so forth. Okay, so this is how we found the percent. Now let me ask this question. It's a question similar to yesterday. If you only have this data, okay, no more. If you only have this table, right? And if I just ask you, well, at any time, I just go and check the oven. What is the probability that the temperature in the oven is between 50 and 55? This is my question. So, well, this is the only data that you have. And the data says that, well, 21.8% of your data, of your temperature, is between 50 and 55. Okay, this is the only data that I have. So by looking at this data, I can say that, well, if you just go and check the oven, the temperature will be between 50 and 55 with probability of 21.8%. Okay. Or if I just ask you, what is the probability that the temperature is higher than 50, the temperature is higher than 50, then what you can do is just sum all these three, okay, which is equal to, I don't know, 0.5, 0.5. I have 2 at 10, 1, 2, 3, 4, 5, 5, 1. That's equal to 40%, right? 40%. So the probability that the oven's temperature is greater than 50 is equal to 40%, or 0.40. Okay? That's because this is the only data that I have. If this is the only data that I have, I can just calculate the probabilities by looking at these percentages. Remember, this is very similar to just finding the integrals under the curve, because that curve just comes from the histogram, and in fact this is how we build a histogram. Okay, now what I do is I just put, okay, histogram just like this. Okay, 30 up to 50, 35 I have one count, 35 up to 40 I have three counts, and so on and so forth. So this is the histogram of this data. So when you just look at this data, well, you can see that, well, the center is at, so the center is at 4550. Okay, so this is my center. So there is a scatter to the right and there is a scatter to the left, and it turns out that, well, the scatter is almost symmetric, which means probably this one just comes from or very similar to a normal distribution. Right? So this is, well, if we just compare it with this data, so just look at this data and then just look at this histogram, right? So this histogram or plotting the variables is a good way of visualizing and hence making comments on your data. So another diagram, another plot is what we call a stem and leaf diagram. Okay, I don't know whether you can read this or not. Stem and leaf diagram. Okay, so stem and leaf diagram is something like this. Okay, so let me ask you, what do you think this one just shows? You have 3 here, 2 here, 3 plus 7, 7, 8. What do you think? What does it look like? So, well, this is, so you might guess that, well, this is 30, okay? So I have a 32 here, right? And here, this is 30 as well, but this one says that, well, just put 30, 31, 32, 33, 34 to the first line, and then 35, 36, 37 to the second line, right? So you have 37, 37, and 38, right? So you have, in the data, you have 3 37s, 1 38, and 1 32. Then you have 3 40s, you see, 40, 40, 40, 41, 42, 43, 43, 44, 4, 4, 4, okay? And this is 45, 45, 45, and so on and so forth. When you just look at this, you can just quickly realize that, in fact, this is very similar to the histogram, but this is a, let's say, horizontal type of histogram, right? It's very similar, right? So just turn this, if you are able to just turn this into in a vertical way, then it will be very, very similar to this plot. Okay? Well, it looks like a horizontal histogram, but as I said, it shows more details than the histogram. But the problem is that, well, it's suitable for data sets that are not very large. So for example, if you have 1,000 many data, just writing them like this is very, very hard. Okay? But remember, we just make histograms for 1,000 data, 100,000 data in our previous lecture. So histogram is good for any number of data, but stem and leaf diagram, well, they can be just used for data which has smaller number of data points. Okay? And one last thing is the box plot. Okay? So box plot, again, it's a good way of visualizing the data. And so it has 5 important statistics. So the minimum data, it's the minimum, but it's not necessarily the minimum that you see in the data. I will just define what the minimum is. So the first part is the minimum. The upper part, so the lowest part is the minimum. This part is the maximum. The center is the median. Remember the median of the data? It's the data at the center, right? This is the first quartile or the lower quartile, which is Q1. And this one is the upper quartile, which is Q3, okay? So we just use 5 important statistics here, okay? So what is minimum and maximum? So this is the plot. Remember, this is the Q1, Q3, this is the median. So what you do is, to the Q3, you just add 1.5 times the IQR. IQR is the interquartile range. Remember, we talk about an interquartile range. It's the difference between Q3 and Q1. So what you do is, over Q3, you add 1.5 times IQR. And from Q1, you just subtract 1.5 times IQR. So this is what we call the minimum of this box plot, and this is the maximum of this box plot, okay? And the data which are outside of this minimum and maximum, later we will see this in the regression, but these data will be called as outliers, okay? Outliers, ayrık noktalar in Turkish. So, well, what you can do with the outliers, you may remove them, but you may not remove them as well. Even if you don't remove them, just be very careful about their explanation. So, or if they are outliers at first, of course, what you should do is you should just check those points whether there's a problem in recording those points, or whether there's a problem in, let's say, writing those points into Excel. So if there are no problems, then try to understand why these points are outliers. Then, as I said, you may remove them or may not remove them, just depending on the context of your problem. Okay. So sorry. So for this, for this particular example, for the temperature of an example, the average the X bar, so this is the sample mean and this is the sample standard deviation. Of course, these are also just some measures for the data, right? So this is the average and this is the deviation around the average. So it turns out that the average is 48.3 and the standard deviation is 6.6. Okay. Right. So, in fact, we are over. We just completed the, let's say, the introduction about the plots of the datas. How do we just measure their properties and so on and so forth. Now we are getting ready for the hypothesis testing. Okay. Okay, so before getting to the new, let's give a 10 minutes break, okay? So I don't want to get started and then give a break. Let's give a 10 minutes break. Let's meet at 13:35, okay? And we will just start with our next point, next slide. Okay. Okay, so know that we are being recorded. Okay. So we are being recorded, that's right. So we will start with okay. So, well, now we will talk about hypothesis testing and confidence intervals, especially for at the introductory stage. We will talk about the mean. Okay. So the first thing that we will talk about is point estimation. Okay. So we will try to estimate, so as I said, so in order to calculate probabilities, we need parameters, okay? So for example, to find the probability of getting two defectives, we need the parameters. The probability of getting a defective. What is the probability that a single item is defective? You need that probability. Okay? Or if you want to calculate the probability of somebody coming into the class and the probability that his or her height is shorter than 165, then you need to know the probability distribution and their parameters. If it is normal, then you need to know their mu and sigma. If it is, for example, exponential, you need to know its beta. If it is uniform, then you need to know what is the minimum and the maximum value of the uniform distribution. So you need to know parameters. But as we say, well, those parameters are, well, most of the time, in real life, not most of the time, but every time they are not known, in fact. You don't know those parameters, right? So what we are trying to do is we need a point estimator, okay, which estimates, which predicts those parameters. Okay, so we need an estimator, which we call a point estimator, which estimates, which makes a prediction, which we can use as its original parameter in our calculations. So a point estimator is a statistic that produces a single numerical value as the estimate of the unknown parameter. So X bar is in fact a estimator. It's a point estimator for mu, right? So mu is the parameter, mu and sigma square are parameters for normal distribution. It's the mean and it's the variance. So X bar is a point estimator for mu and S square is a point estimation for sigma square. Now let me put a tick here. So mu and sigma square. Mu and sigma square, we have two meanings for them. The first meaning is, well, they are parameters of the normal distribution, okay? Parameters of the normal distribution, right? The normal distribution has two parameters, mu and sigma square. And what does it represent in normal distribution? Mu is the expected value of normal distribution and sigma square is the variance of normal distribution. Second, well, mu and sigma square they show mean, okay, and variance of all distributions, right? So for any random variable, expected value of x can be shown by mu of x. So what we say is that, remember from your probability course, expected value of x is equal to mu, right? And variance of x is equal to what? Variance of x is equal to sigma square, right? So this is mean and variance for all distributions, okay? You see, so first they are the parameters of normal distribution, right? And they show the expected value and the variance of all distributions. Çok özür dilerim arkadaşlar. Efendim, buyurun. Pardon. So they are mu and they just show the expected value and the variance of all random variables. So in fact, this shows the power of the normal distribution. The normal distribution is so powerful. It's very effective on the probability and statistics so that we use their parameters as the mean and the variance of other distributions, okay? So again, normal distribution is so important, it's so influential, it's so powerful that we use their parameters as the mean and the variance of every other random variable as well. Okay. So x bar and s square, well, they are the mu and sigma, they are the point estimators of mu and sigma square. Okay. Um, okay. So for example, for Poisson, the mu of which is the expected value of that random variable is lambda, and sigma square, the variance of that random variable is equal to lambda as well. So lambda is the parameter of the Poisson. Remember, for binomial, the parameters are n and p. So the expected value of a binomial random variable is n times p, right? And the sigma square, the variance of a binomial random variable is n times p times q. Okay. Well, so it's intuitive that mu shows the expected value or the average of a random variable. It's very intuitive that x bar is an estimator, is a point estimator for mu, okay? Because it's the average of the data. S square, well, that's also intuitive. Not very intuitive. For example, if I just ask you before introducing you x bar and s square, if I just ask you, well, mu is the expected value or the center of a random variable. So, well, how can you estimate it from the data? You may say that, okay, hocam, you can just take the average of the data and it's the estimator for you. Okay, that's easy. But if I just say, well, sigma square is the variance, it just shows you the variance around the mean. How can you estimate it from data? Well, you may you may think that S square, you may find that S square is the estimator. You may not, it's not very obvious. So it turns out that, well, for the parameters of the distributions, for example, for P, for lambda, or for other parameters, for example, we have beta distribution, we have gamma distribution, they have different parameters, okay? So it's not always very obvious to find estimators for the parameters. For mu and sigma square, okay, we know them. Or for example, if we are trying to find um, for example, let's say the the probability of getting a defective item. So if you don't know the probability and if you want to estimate them with a point estimator, what you can do is go and take thousand many items from the factory, just count how many of them are defective and divide the number of defectives by 1,000. Okay, that's very simple. So that's the point estimator of your what? Of your defective probability, okay? But as I said, there are some other distributions, the gamma distribution, beta distribution, there are several other distributions. Well, it's not very obvious to find the point estimators. We have some ways to find them. One of them is called the maximum likelihood estimator, but it's not our, let's say, it's out of our scope, but just know that, well, there are some ways to find the good estimators, okay? Well, what do we mean by a good estimator? For example, X bar. Remember X bar? X bar is an estimator for mu, and S squared is S squared is an estimator for sigma square. Well, how do we know that S squared is a good estimator? How can we know this? Or how do we know that X bar is a good estimator? Well, there are two, let's say, quality indicators for estimators. The first one, it should be unbiased. What does it mean being unbiased? Being unbiased means that, well, remember, x bar is a random variable. If it is expected value is equal to the parameter that you want to estimate, then that's an unbiased estimator, okay? Or, for example, for S square, the expected value of S square, remember S square is a random variable. Like every random variable, it has what? It has a expected value and the variance. Its expected value is equal to sigma square. If the expected value of estimator, again, recall that estimators are random variables. If their expected value is equal to the parameter that you want to, let's say, estimate, then they are called unbiased estimators. What does this mean? So if you are able to take too many of them, so for example, if you are able to just find, for example, 1,000 many or 10,000 many X bars, then their average will be very close to mu. Okay, so this is something good for the estimators. Their expected value is equal to mu. So this is the first thing about the estimators. Okay, so it should be unbiased. Or let's say being unbiased is a good performance indicator for an estimator. And the second one is it should have minimum variance. Okay. So remember, for every random variable, we have two measures. One, where is the center? Second, how is the data scattered around the center? So these two properties says that the average of the data, the center of the data should be equal to mu itself, and it should not deviate too much around that mean. Okay, so a good estimator should have a minimum variance. So let's look at this part. So let's see this. So this is an accurate but not precise estimator. This is a precise but not accurate estimator. This is the accurate and precise estimator. What does this mean? So this one, okay. So this one says that so for example, let's talk about our X bar and mu. This one says that expected value of, let's say this is an estimator. Let's say this is not X bar, but let's say this is something like X. Okay, sorry, let me just erase this. Okay, let me say I have an estimator and its name is mu hat 1. Okay, so in general, if you have a shapka, if you have a hat here, it means that it's an estimator of the parameter mu. Let's say I have an estimator which is mu hat 1. This one shows that the expected value of mu hat 1 is equal to what? It's trying to estimate mu, hence this is equal to mu. You see this, if we just take the average of these dots, okay, on the average, it is very close to the red point. So this red point is mu, okay, this is mu, this is mu, this is mu. So in fact, this is just like a gun, okay? So mu1 hat, this is a gun. What you do is you just shoot with this gun to just hit this bullseye, okay? Well, at the first shoot, you just hit here. At the second shoot, you just hit here. At the third shoot, you just hit the other place, and so on and so forth. Okay. So on the average, you just shoot around this bullseye. Okay. So I have an standard deviation of this mu1 hat. What does this mean, standard deviation? As you see, um, the shoes that you have is around this point. But if you just compare it with this one, right? This one, let me say this is mu3 hat. This is mu3 hat. So I have expected value of mu3 hat, okay, mu3 hat. What does this mean? This means that, well, I have an estimator for mu. This is different than the first one because this is mu1 hat and the other one is the mu3 hat, right? This is mu3 hat and this is mu1 hat. So this is different than the previous one. And it turns out that the expected value of mu3 hat is equal to mu as well. Why? Because again, this is a gun. You are trying to shoot this bullseye. It turns out that, well, it shoots very well, right? It's just around that bullseye. Around this bullseye. And when you compare it with the mu1 hat, it turns out that, well, it doesn't scatter around the red point too much when you just compare with the mu1 hat, okay? So you can just clearly write sigma mu hat 3 is smaller than sigma mu1 hat, okay? So this one and this one, both of them are unbiased. Why? Because on the average, they are shooting the right place. But it turns out that, well, this one has a smaller variance. Okay, this one has a smaller variance, which means it just shoots much more closer to the red point. Hence, both of them are accurate, which means, well, they're unbiased, but this one is not precise, which means, well, okay, it's standard deviation. It's scattered around the center is a bit higher than this one. This one is accurate and precise. This one is accurate but not precise. So which means high variance, okay? High, let's say variance, which is high sigma, okay? Let's look at this one in the middle, the one in the middle, right? So here, it turns out that, well, sigma, mu, let's say this is mu 2 hat. What can you say about the sigma mu 2 hat? Well, the scatter around its center is smaller than, right? Smaller than mu 1 hat. That's good for this one, okay? That's good for mu 2 hat because its variance is smaller than the first one. But the problem here is that it's precise, okay? Its standard deviation is small, but the problem is that it's not accurate. What does it mean? Well, you are shooting the wrong place. You should just hit here, but you are just hitting here. Okay, so the gun, the aim angle of the gun has a problem. It's not shooting the right place. It's just shooting somewhere above it. Okay. So what you want estimator to be is it should be accurate and precise, okay? Just like this one. What does this mean? Well, it should just hit just the center, and the deviation around the center should be just very small as possible. Let's say not very small, but as small as possible, okay? Um, so let's look at this one, okay? Let's look at this one. So here, this is sigma 1 hat. Okay, so let me just compare it with this one, sigma theta 1 hat, sorry. So this one, theta 2 hat, theta 1 hat. So as you see, theta 1 hat has a distribution whose center at theta. So theta is the parameter that you want to estimate. Okay, you can think of theta as your mu, and you can think theta 3 hat as your mu hat. So let's say this is mu 3 hat. I'm not sure whether it's mu 3 hat or not. So which one is the best one? Sigma 1 hat. Why? Its center is at mu, okay? Its center, sorry. Um, its center is, sorry. Its center is at mu, and as you see, its deviation is smaller than sigma 2 and sigma 3 because it has a peak at theta, and it just goes quickly down to the left and to the right, okay? So theta 2 hat, it has a, let's say, it has a thick tails, okay? It has long tails or thick tails at both ends. So when you just compare with your previous slide, this one, so which one is mu 1 hat, which one is mu 2 hat, and which one is mu 3 hat? It turns out that mu 3 that was the best one. So I can say this is, sorry, so this is mu 3 hat, right? Theta 1 hat is mu 3 hat, and theta 2 is mu 1 hat, okay? Mu 1 hat. And theta 3 is what? What else? I have mu 2 hat, right? Okay, that's great. Okay, any questions so far? Let me open the chat. Okay. Okay. Any no questions? Okay. Now we will start talking about hypothesis testing. Okay, so this is the base for statistics. Okay, so in fact our whole statistics course will be talking about hypothesis testing. So if you just feel comfortable about this thing, then you will be comfortable at your exams, at your future work, at your future studies, at your future courses as well. Okay. So okay, if you can open your voice, if you can open your microphone, you're welcome. Okay, because I like just making some conversation on hypothesis testing when I was in the class. So, well, this is my conjecture. The average height of students in Özyeğin University is 170 centimeters. Okay, what can you say about this? Or how to test this? How can you say whether this is true or not? First, do you agree with this or not? Okay, this is my question. Hmm. Do you agree with this or not? Okay, guys. Is the average height is so? So, in fact, this is my question. Well, the average height of all of the students in Özyeğin University is 170 centimeters. This is why I conjecture. This is my, let's say, this is my assertion. Okay, I have I have a feeling like this. What do you think? Is that true or not? Yeah. Is that true or not? I mean, well, what do you think? Okay. So do you think that what is it higher than 170 or lower than 170? What do you think? So I cannot see you, so I don't know your height. So if we were in the class, then I was able to see you and I can just make some other conjectures, but now I cannot see you. So okay, Ilayda. Um, I'm just I just say that well, I think the average height of the students in Özyeğin University, okay? So if there are 10,000 many students, their average is 170. In other words, I say that, well, I say that your height, okay, the distribution of your height has a mean of 170 centimeters, okay? Do you agree with this? Do you think it is larger than this or smaller than this? Because you know your friends, right? You know, you just living there, so you know better than me. So what do you think? Is this true or not? Okay, sorry. Okay, so Sinan says that, well, the average is above 170. Okay, he says that, well, mu is not 170, but it's something above that, right? So Elijah says it can be true, 170. Okay. Any other guess? Any of you who says that, well, it's not 170, but it's smaller than that one? I guess there is none. Okay. So I understand you. So it may be 170, and you say it may be greater than 170. So how to understand this? Okay. So if I ask you, well, Ilayda, Cenk, okay, Meltem. So just just uh, try to understand whether the real mean is 170 or not. Assume that I just give you an assignment for the next week, and I just ask you, well, try to understand whether mu is really is equal to 170 or not. How can you understand this? How can you test this? How can you let's say, experiment this, whether the real mean is equal to 170 or not. So Malcolm says, we cannot say true or false before we take sample. So shall I think of this as an answer to my current question? Malcolm. Nasıl test edersiniz? Mü eşittir 170 dedim. Bana neyle dönüp hayır hocam 170 değildir, evet hocam 170'tir diyebilirsiniz. Ne yapabilirsiniz? Okay. So that's great. İsmet says that, well, I can take random samples, right? So in our class, I don't know how many participants do we have. There are 6 participants. So what we can do is, we can just ask 8 of you, okay, 6 of you, then take the average and compare its mean, the population, it's the sample mean with 170. Or if you have, so probably you have much more larger number of friends than 5 or 6, okay, you can ask your friends, what is your height, what is your height, what is your height. You can just collect, I don't know, 30 or 40 many guys, the height of 40 or 30 or 40 many guys, take the average of them and compare it with 170. Okay, so great. So let me ask you this. So that's expert, right? So you just ask, for example, I don't know, 20 of your friends, and it turns out that X bar is equal to 171. Now, do you say that, Mehmet Hocam, well, mu is not equal to 170 because I found X bar as 171? Or will you say that, Hocam, it can be 170? What do you think? Can you say that, well, mu can be 170 or it cannot be 170? It should be something larger by just looking at this X bar. What do you think? And let me ask you something. So I think you are in a place, in a crowded place. There are lots of voices there. That's because that's that's that's the reason you don't open your microphones. Is that true? Or you don't want to talk at all? You just feel comfortable in writing? Because in my view, in my part, it's a bit weird. I'm just talking and you're just writing, so that's a bit weird for me. Okay, again the question. So I said the real mu. Okay, the standard should be visible, I think. Okay, Ismail, that's great. Okay, so Ismet says, Ismet Sinan says, let's say, we should just calculate the standard deviations, like how far 170 could deviate versus how 171 is deviated around our random sample. Okay, that's a very good point. So what you can do is, okay, let me just ask you this. So if X bar is equal to, let's say, 100, and let's assume that you just ask, for example, 20 of your friends, and X bar turned out to be 183. Will you still say that, hocam, the real mu can be 170 centimeters? That's a clear no, right? Because, well, this is 183. This is what I see, okay? But the X bar is the data. That's the data that I see. And 170 is my conjecture. Well, it turns out that, well, there is, what can we say? There is a big gap. There is a big difference between X bar and mu, right? So if you just see X bar as 183, then you will probably say that, hocam, well, probably it's not 170 centimeters, okay? But for example, if we just find X bar as 170.3, for example, then will you still say that, hocam, X bar is different than mu, so that, well, mu is not equal to 170? Well, you just take a sample of, okay, exactly. There is a small error here, right? You just take a sample of too many people. So the average of them is 170.3. This is a random variable, right? So if you just take another too many people, their X bar will be something different. I don't know, 169.5, for example, or 183, for example. Um, so your result, let's say your decision based on this X bar is different than your decision based on this X bar. Okay? So what is the thing that we are just checking? The thing that we are checking is, in fact, many of you just said this. We are just looking at the error, or we just look at the deviation. Okay, so the difference here is what? The difference here is 13 centimeters, but the difference here is what? This is 0.3 centimeters. Okay, so in fact, what we are looking at is my conjecture and the real data. If the difference between the conjecture and the real data is large, then we say that, well, there is a problem with the conjecture. Why? Because, well, this is the data, right? This is the data that we see. That's because I have to suspect my conjecture. Okay. But if the difference is very close to each other, you may say that, well, mu is equal to 170 centimeters is fine, because if students has a mean like this, then I can see an X bar like 170.3. Okay, so in other words, a population whose mean is 170 centimeters may produce a sample. It may produce a sample. You may observe a sample whose X bar is 170.3. Okay, that's great. Um, okay, so in fact, so where can we say, okay, you are right, mu can be 170 centimeters. And where can we say, hocam, well, there's a problem with your conjecture. That's not probably true, okay? So where is the threshold? At 171, 173, 175. For example, let's say 170. Okay, let's say this is your mu, let's say, or x bar, it can be x bar, plus minus, let's say 3. Okay, well, let's try to see whether it works. 170 plus minus 3. So what you can do is just put a plus minus 3 to the right of the mean. Well, if you just put something like this, just 3, well, then there will be a problem in other questions. How? For example, if I just said you this one. So I assume that the average, let's say, income of doctors in Turkey is, let's say, I'm just making it up, 30,000 Turkish liras, okay? The monthly income of doctors, the average income of doctors is 30 Turkish liras, okay? Well, then by just looking at X bars, plus minus 3 will not work, right? Because here that's 170, here that's equal to 30,000. So 30,000 plus minus 3, 170 plus minus 3, that's not a good start, right? So how can we change this? You might expect to say something like this: 170, right? For example, plus minus, let's say 10% of 170, right? This is much more better, okay? Understand? Because what you do is you just put a plus minus error term, or let's say an interval, which is based on the, let's say, which is based on the, let's say, the mean value. So if this is 170, you just multiply by 10%, that's 17. If it is for you 30,000, then it will be 10%, it will be 3,000. Okay, so this will work, whatever you just write here. So is it fine now? I can just write your mean. Okay, let me just write it somewhere here. Mean plus minus some percent, I don't know, let's say 5% times mean. Is that right? Is there any problem with this? Um, okay, so let me just um, okay, let me just show you something. Let me just recall you a slide that we have seen before. What is that? Hmm. So let's share my screen again. Just look at this one, guys. So here, so let's just look at here. Let's say, so this is the mean, let's say, okay, 60, 60. So if I just say, for example, 60, okay, 60, let's say plus minus 20%, 20%, then what is the interval now? 60 minus 20% times 60, of course. So this is 12. 60 minus 12 is 48. 60 plus 12 is 72. So what is 48? 48 is somewhere here, okay? And what is 72? 72 is somewhere here. So can you see this? Well, this interval almost covers all of the observations that we have, right? Let's say it covers, I'm just making it up, almost 99% of your observations, right? Let's come here. Now, 60 plus 72 and 48. That's what it is, 48. Just look at here. Now, this portion, does it cover 99%? Well, no, right? So when you just look at here, it covers, let's say, at most 60% of your observations, right? So writing your mean plus minus some percent times mean, well, it works different in different distributions. Where is the difference? Why do we have such a difference? The difference is due to what? The difference is due to, sorry, the difference is due to the variance, okay? So if you have a high variance, then the data is dispersed around the mean, hence plus minus some percentage of the mean will cover less than a distribution who has a low variance. So what you have to do is, what we will try to do is, we will just try to find an interval like this, but we will just employ the standard deviation in this interval as well, okay? Not only the mean, but the percentage, we will also find, try to find a way which just employs the standard deviation in this example, right? So I have just few things to say. Okay. So this is the first example that we have about hypothesis testing. Well, um, so there is a random sample of 100 recorded deaths in Turkey during the past year. And well, the X bar of 100 many people, so what they do in Zincirlikuyu is that they just look at the ages of death. Okay, there are 100 many people. They just randomly pick 100 many people and recorded their ages and take the average of their ages. It turns out that the average is 71.8 years. Now, I want to test whether the mean life today in Turkey is 70 or not. So I just want to test whether the average life of people in Turkey is 70 or not. Okay? So as you see, there is a difference of 1.8. Is it large? Is it a large difference? Is it a small difference? We will try to see. First, assume that the population standard deviation is known. We will later relax this assumption and say that, well, we don't know the standard deviation. But as a starting point, let's assume that we don't know, we just know the standard deviation of people's life in Turkey. That's a bit weird, okay? Because you don't know the real mean, but you know the real sigma. But as I said, as a starting point, we just assume that you know the standard deviation of people. So what can we say about this conjecture? Okay. So what we will do is we will just use the hypothesis testing procedure to test this conjecture, to test this, let's say, um, this this thing, let's say, okay, this assertion. So a statistical hypothesis is an assertion or a conjecture concerning one or more populations. So how to do this? Well, we have what we call a null hypothesis and we have an alternative hypothesis. So the null hypothesis says that, well, the underlying mu, okay, the population's mu is equal to 70. And the alternative hypothesis says that, well, the alternative hypothesis is the counterpart of the null hypothesis. So null hypothesis says that mu is equal to 70. Alternative hypothesis says that mu is not equal to 70. Okay? So there are two decisions. What you can do is you can reject the hypothesis and say that, well, I reject. That's where you just say that, hocam, well, mu is not equal to 70, right? You are wrong. So there are two decisions. Just reject H0 in favor of H1 because of sufficient evidence in the data. So what does it mean? So you just remember in our example X bar, your data says that the average lifetime is 71.8 years, right? Either this data is, you will find that this data is clearly far away from 70, which means that, well, this data is a sufficient evidence, okay, to reject this hypothesis, okay? Or you will fail to reject H0. You cannot reject H0 because this X bar is not very far away from 70, which means, well, this evidence is insufficient, okay? Which means, well, the data that I have here is not enough for me to reject this hypothesis, okay? So recall X bar is 71.8. Well, we said how close. So we said that, well, if it is close enough, we will reject. If it is close enough, we say that we don't reject it. But if it is not close enough, we will reject this. But how do we just find the closeness? Well, the clever way is just assume that the null hypothesis is true. What does it mean? So we will assume that or if you are just making the test, you will assume that Mehmet Hoca's conjecture is true. What does it mean? Well, people in Turkey really has a mean life of 70. Okay? You assume that this is true. What does it bring to us? What does it bring to us? Let's write what we have. Mu is equal to what? 70. So this comes from the hypothesis. We just assume that mu is true, okay? The null hypothesis is true. What is sigma? Sigma is equal to 8.9, okay? What is n? Number of observations. N is equal to 100, okay? Now, just think of x bar. X bar is a random variable, okay? Now, what is the distribution of x bar? Do you know it? The distribution of x bar is normal, approximately normal. Remember, why? Because we have a central limit theorem. It's approximately normal. So it's approximately normal. What are the parameters of sigma? Well, it's sigma, it's standard deviation. I know from my previous calculations, it's sigma divided by root n, which is equal to sigma divided by root n. That's equal to 8.9 divided by 100, which is 0.89. Okay, great. How about its mu? Mu of x bar. Do we know it? Well, at the beginning of the question, we don't know it. But now we assume that null hypothesis is true. Okay? So if null hypothesis is true, then mu is equal to 70. If mu is equal to 70, I know that mu of x bar is equal to mu of the population. Hence, mu of x bar is equal to what? Mu of the population, individuals, that's also equal to 70. Well, I have a great result now. What is this result? This result is that I know the distribution of x bar. That's great. I can plot it. This is the distribution of x bar. What is the center? What is the center? Center is 70. What is the standard deviation? The standard deviation is 0.89. Okay? 0.89. Right? Okay. Then what is left? This is the distribution of x bar. Okay? This is the distribution of x bar. Oh, I have this. This is the distribution of x bar. That's great. That's great. Now, the only thing that is left is this. This is my observed random variable, okay? This is what we will call as the x bar observed. This is x bar observed. You just observe that your sample's x bar is 71.8. So what we will do is just put 71.8 here, okay, here. It's somewhere here, right? And try to understand whether observing 71.8 has a small probability or not. Okay, just put it here, 71.8. Let me just change the color. Let's change the color, 71.8. Okay, just try to see whether this value has a small probability or not. Or in other words, let's try to understand whether this value in this probability distribution, is it an extreme value or not? Okay, extreme value. Bu dağılımda böyle bir dağılım olduğunu biliyorum X-bar'ın. Gözlemlediğim bu değer bu dağılıma uyuyor değil mi? Bu değer bu dağılımda yerine koyduğumda acaba çok uç bir değer mi? Çok ekstrem bir değer mi değil mi? I need to decide on this. Okay? Whether this is an extreme value or not. How to decide this? So how do we define a point to be extreme? Well, it's given as the significance level, okay? So in each hypothesis testing questions, we are given a significance level alpha, which says that, well, to the right of your distribution and to the left of your distribution, alpha over 2 of your random variables are extreme, and to the left, alpha over 2 of your values are extreme, okay? So for example, if the significance level is given as alpha is equal to 0.10, right? It means that you just leave an area of 5% to the right, and you just leave an area of 5% to the left, and you say that the observed x bars, which the observed x bars which fall into this region or into this region are extreme values, which make me reject the null hypothesis, okay? So if our x bar observed is there, then we can just reject H0. In general, we just pick alpha as 0.01, 0.005, or 0.1. These are the general values, okay? Um, okay, okay. Let's stop here, don't overshoot, okay? So tomorrow we will have a recitation. You will just solve questions about these, okay, in the recitation. And next week we will continue with the hypothesis testing, okay? So thanks everyone for joining me. I will just stop recording, okay?